Hello students, welcome to this lecture. In this lecture we're going to talk about data compression. And we'll start by discussing how we can compress text. And the first example that we can talk about is from history. There used to be a way of communicating through the telegraph. Basically, it's a cable-based devices. One device is in one place, and then there is a cable connecting these two devices, and you can send sound signals over the cable. And in the telegraph, people used Morse code. Morse code. Basically, you're probably familiar with the Morse code. It uses short and long signals. So basically a short sound and long sounds, but we can think of it as a short bar and long bar in our code bars. So theoretically speaking, we can use zeros and ones to represent short and long signals. So what does it mean? It's pretty much a binary code for text. Binary code for text. That's what it means. Binary code for text. For example, letter E was represented by a short sound. Short sound. And in the Morse code, it's dots and dashes, right? So short sound, so it was one dot. And for letter S, it's a short and short. Short and short. So it's dot, dot, and dot. That's for S. And for O, for example, it's long, and long. And usually for long ones, these are dashes. So 3 dashes means long, and long. So why E has just one symbol? Because E is the most common letter used in English language. So the most commonly used letter, right? And it's in English language, so in other languages there are different letters. So it has the shortest possible way of being used inside of the Morse code. And our famous signal, for example, famous symbol, SOS, right? That ship sends out when they in trouble. It's short, long, short. Famous signal in C. But what does it teach us? This teaches us that for some letters we use 1 bit of information, but for some letters we use 3 bits of information. So we use different lengths for different letters. So this would be called variable length codes. Variable length codes. And that's what we want to focus a little bit right now. So what does it mean, variable length code? That means you encode, so encoding for different letters have different lengths. Encoding for different letters has different lengths. That's the idea of the variable length code. So we talked about one way of using it that was Morse code. Then what is the idea of the data compression, right? That's the name of the lecture. Data compression, what's the focus? The focus is what we're going to do when we're talking about data compression. The idea is that the compression algorithm converts the data from being long and easy to use into the data that is squeezed in and optimized for compactness. So basically, we can write it like this: a compression algorithm, a compression, oh, a compression algorithm converts the data, from easy to use form to the optimized form optimized for compactness. What would be the most famous example? There are a couple. So we talked about some of them, like remember JPEG, right? JPEG, but it's not about text, it's mostly about pictures. But for text, the most famous example is probably zip files in the computer. That's one of the famous examples. You take your file, you convert it to a zip, and if it's a text, it's really optimized for text. Pictures, if you take them and convert to zip, there is not much optimization because pictures are already optimized, like JPEGs. If you convert them to zip file, then there is no much gain. But for text, there is a lot of gain. We're not going to focus on zip files, though. Our focus will be on a bit more interesting application about DNAs, right? And DNA, it's something that keeps information about who we are, and the translation is deoxyribonucleic acid, right? and A, right? That's the translation. So what is the idea of the DNA? DNA is just basically a sequence of 4 acids, right? If you're familiar with biology, which I'm not, a little bit, just tiny bit, no, I don't know much about it. And so DNA is a sequence of 4 nucleic acids arranged in various orders. That's the idea of the DNA, and usually for acids, there are 4 acids. So for DNA, there are, sorry, I didn't say it right. There are 4 bases, A, C, G, and T. And A stands for adenine. C stands for white tyrosine. If I pronounce it right, I'm not 100% sure. V9 for G. It's not crazy important for us just to keep track of things. And high 9 for the T. And the order of bases, determines which proteins are constructed in a cell. Which proteins are constructed in a cell. And the most common one is actually A. A is the most common one. This is the most common one, I think. All right, so how many bits do we need? How many bits of information do we need? For what? Do we need to store each base? So there are a couple of different ways to approach it. We can made up way. So we're making it up. So what is the idea? The idea is really simple. Since we have 4 acids, we need 4 choices. And 4 choices, let's try to think about it. If we need 4 choices, but we have bits of information in the computer. So in other words, how many bits? For 4 choices? So let's try to think. If we have 1 bit, it has 2 choices. If we have another bit, it has 2 choices. Why 2 choices? Because it's either 0 or 1, right? It's 0 or 1. So if we multiply this, we're going to get 4 choices. So that means, this means we need 2 bits. For made-up code that we create. So let's do the made-up code itself. So made-up code. So we can assign A to be 0, 0. We can assign C to be 0, 1. We can assign G to be what? G to be 1, 0, and T to be 1, 1. But as you can see, for each letter we use 2 bits. For each letter, so it's a fixed length code. This is a fixed length. It's not variable length like we would like to discuss. So let's look at the example how to use fixed length code. Examples in this part will be really easy, and assignments will be really easy. It's just important to understand the idea of the variable length codes. So first example, if we have something like A, C, T, G, G, A, T, A, C, C, T, and G. So the assignment says encode it by using our made-up code. So then it's relatively simple. We take our sequence, and we probably move to the next page. So this is our sequence, and we're gonna plug in the code. Let's look up the codes. The codes are here, so maybe we should also copy it so we'd have nearby. So we take this and put it here. Okay, so we have our codes, we have our sequence, so we're ready to code. So for A, we're going to put 0, 0. For C, we're going to put 0, 1. For T, we're going to put 1, 1. For G, we're going to do 1, 0, then 1, 0, then 0, 0, then 1, 1, 0, 0, 0, 1, 0, 1, 1, 1, and 1, 0. And this is the code that we're going to use. This is the code we're going to use. All right, so it's easy to encode with the fixed length code, and it's easy to decode back from the fixed length code. All right, so let's do an example where we're decoding. This was encoding, right? This is encoding. This is encoding. That's the next example says. Next example, the assignment says decode 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 0, 0, 1, which was encoded with our made up code. So this sequence was encoded with the made up code, and we would like to decode it. So we're doing decoding now. Decoding. And to do the decoding, we will use the code. We'll use the code, and we're going to take this sequence and we'll try to decode the sequence. So since our code is a fixed length code, fixed length code is really easy to decode. Fixed length code. So with decoding, we're gonna chip off 2 digits at a time, and use the table. I'm gonna use the table. So let's try to do that. So we chip off first 2, it's 0, 0 from the table, we put A. Then we chip off 2, we put A. Then we chip off 2, 0, 1 is C. Then 1, 1 is T. Then 1, 0 is G. 0, 1 is C. Then 0, 0 is A. And 0, 1 is C. So our answer is A, C, T, G, C, A, and C. So for the fixed length code, it's really easy to encode, and it's really easy to decode by just chipping off the length of the code. Right? You take 2 digits at a time, you chip it off for this particular code because each letter is 2 digits long. But again, we're not really focused on the fixed lengths. We're mostly interested in a variable length code. So the question is, is it possible to use variable length code? Length code to encode DNA. to encode DNA. We saw the Morse code, right? We saw the Morse code, so we need to use similar idea. And what do we want to achieve? We want to save some space. We want to save some space. And why do we do that? Because these DNA sequences are crazy, crazy long. And if you store a lot of them, it takes a lot of space in the computer. So the idea is to store some to save some space. So one possibility we can use is this kind of a code. One possibility, and in the homeworks you might be provided with a different possibility, but for a class, let's use this code. A is the most common acid, so let's get the shortest code, so A gets 0. C gets 1, 0. G gets 1, 1, 0. And T gets 1, 1, and 1. So we have length 1, we have length 2, and we have length 3. So let's try to go back and take our previous assignment of let's do the new one. Let's do the new one. So that the example says, and again, A is the most common one. So the assignment says encode A, C, A, T, A, G, C, C, and A with the variable length code. With the variable length code. So like always, we take our sequence, we move it to the next page because we ran out of space. And this is our sequence here. Probably we will also need to grab the code. So we'll take the code. Okay, now we're ready to encode. So encoding part is really easy. So you take letter and you put the appropriate digits for the letter. So 0, then 1, 0, then 0, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, and 0, and 0. And this is the code that we have created. So how many bits we used? We used 18 bits. We used 18 bits when I'm sorry, maybe not when, but maybe with the variable length code. With the variable length code. So what would happen if we would use made-up code, which is fixed length code? If we would use fixed length code, and for the fixed length codes we can use made-up code, right? The one that we made up, right? And this code uses 2 bits for each letter, 2 bits for each letter. If we would use fixed length code, we would need how many bits, right? How many bits? But let's count. How many letters do we have? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters. We have 11 letters. So we would need 11 times 2 bits for each letter. So we would need 22 bits. Okay, so we used 18 bits, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 bits with a variable length code, and we would need 22 bits with a fixed length code. So it's 4 bits advantage, 4 bits advantage. So you might say we didn't really win much, but actually if it's huge amount of information, then we win a lot. Like if we would divide 4 bits of advantage, so it's 4 out of 22, right? 4 out of 22. So 18% advantage, right? Approximately 18% advantage. And it's a lot if you're dealing with billions and billions of bits of information, right? The last thing we need to discuss in this lecture is how to decode with a variable length code. We did the decoding with a fixed length code, which was easy. We just chip off 2 bits, but here it's not really clear. It's not really clear how to decode. So let's do this and finish this lecture. So decoding with variable length code, It's a little bit more complicated than the fixed length code. So let me remind you, our table is A is 0, C is 0, 1, G is 1, 1, 0, and T is 1, 1, 1. You might say that this is really Saint's choice, but you will see actually mistake here. Should be 1, 0. Otherwise, we won't be able to stop. So what's the idea for stopping? The idea for stopping or chipping off bits is to look for zeros. If you see 0, you stop. Or if you count 3 ones in a row, then you stop. So that's our strategy. Let's put it on the paper or on the screen in our case. So if you find 0, 0 is always a terminator. That's how it's called officially. Terminator, right? Like in the movie, it kills everything. So it stops your movement, right? So what does it mean? It means stop, right? It means stop. And second thing that you have to watch for is 3 consecutive ones in a row. So that must be T. This one. That's all. We'll watch for 0, but if we don't see 0 and we counted 3 ones, we stop. Let's do an example, and this would be the end of this lecture. So example says decode 1 0 0 0 1 1 0 1 1 0 1 1 1 0 0 1 0 1 1 1 0, which was encoded with A, which is 0, C, which is 1 0, G, which is 1 1 0, and T, which is 1 1 1. And like before, we take our sequence and we'll try to chip off some bits from it. So let's try to do that. So we take our sequence and we go through the procedure. So as soon as we see 0, we stop. So we're basically moving until we see 0. So 1 0 in this sequence, it's C. Then if you see 0, you stop. This is your A. If you see 0, you stop. This is your A. You go until 0, so this is 1 1 0, so this is G. 1 1 0, this is G. 1 1 1, but this is exactly 3 ones in a row, so this is T. Then you see 0, this is A. This is A, 10 is C, 3 ones it's T and A. And that's your answer. So answer C, A, G, G, T, A, and C, T, A. And that's our answer for the decoding part. All right, so we talked about two examples how to compress text, Morse code, and DNAs, and then we'll talk about numbers in the next lecture. I'll see you then.